Now let's discuss short circuit test. From open circuit test, the shunt branch elements of approximate equivalent circuit of transformer are found, that is R0 and X0 are found from open circuit test, as well as the transformer iron losses are found from open circuit test. And from the short circuit test, the series branch elements of the approximate electrical equivalent circuit of transformer are found, that is R01 and X01 or R02 and X02, depending on the side at which the meters are placed. And also from short circuit test, transformer copper losses are found. Therefore, short circuit test is used to find out the series branch elements of the transformer and the transformer copper loss. Open circuit test is preferred on LV side with HV open, whereas short circuit test is preferred on HV side with LV side short circuit. Therefore, first let's discuss how to perform this short circuit test and how to find these R01 and X01 or R02 and X02, and also let's find out what happens if the short circuit test is performed on other than the preferred side of the transformer. And let's also discuss why UPF wattmeter is to be used in short circuit test to measure the input power. Short circuit test is preferred to perform on HV side of the transformer with LV side short circuited. LV side of the transformer is short circuited with a thick wire or ammeter. To measure the input power, here UPF type of wattmeter is used, and to measure the input current, MI type ammeter, and to measure the input voltage, MI type voltmeter. And these meters are connected like this, and the supply is given through a single phase variac. Procedure: the first step is connect the circuit as shown in figure, and the second step is by varying variac apply rated current, and then the third step is note down meter readings and find out R01, X01 or R02, X02 and copper loss of the transformer. So connect the circuit as shown in figure, and we must short circuit the LV side of transformer with a thick wire, or we can short circuit with an ammeter. And then by varying variac we must apply rated current here, whereas in open circuit test by varying variac we are applying rated voltage. Here we must apply rated current. So rated current is found out by rating of the transformer divided by the HV side voltage. So vary the variac till the ammeter reads rated current, and this current is represented with ISC, and voltmeter reading is represented with VSC, and wattmeter reading is represented with WSC. And here you must make a important note that the rated current is obtained at 4 to 5% of rated voltage. That is, if suppose the HV side voltage is 100 volts, then the rated current is obtained at 5 volts. That is, very low voltage applied to the HV side. Wattmeter reading is represented with WSC, which can be equated to ISC whole square into R01. That implies R01 is equal to wattmeter reading by square of the ammeter reading, and the ratio of voltmeter reading VSC by ammeter reading ISC gives you the impedance Z01. As here Z01 and R01 are known, we can find the X01, which is equal to root over Z01 square minus R01 square. Now let's see how to find the copper loss of the transformer. It is known that total input power is equal to total output power plus losses, and in transformer losses are classified into major losses plus minor losses, and as minor losses are very low, these can be neglected, and the major losses are copper losses and iron losses. From the losses topic, it is discussed that copper loss depends on the current and iron losses depends on the voltage. In short circuit test, as very low voltage is applied, that is 4 to 5% of the rated voltage is applied at the input, so the iron losses are very low, and because of which we can neglect these iron losses. And here in this short circuit test, the output terminals are short circuited through an thick wire, which means the terminal voltage V2 is 0. So terminal voltage V2 0 means the output power V2 I2 cos phi 2 is 0. So this is 0, which implies the total input power is equal to copper loss of the transformer. And here in short circuit test, we are making use of UPF type of wattmeter to measure the input power. So from this relation, as input power is equal to copper losses, which means that the wattmeter reading will indicate the copper loss of the transformer. This is how the series branch elements R01 and X01 and copper loss of the transformer are found from short circuit test. Now let's discuss what happens if SC test is performed on other than the preferred side. This is the preferred side of the transformer at which the short circuit test is to be performed. And now we are discussing what happens if the short circuit test is performed on other than the preferred side. That is, if the test is performed on LV side with HV side short circuit. To understand that, let's consider an example. Let's take the transformer with 3300 volts by 220 volts and 33 kVA rating. For that, let's consider two cases. That is, if test on preferred side and if test on other than preferred side. That is, here on HV with LV short circuit, and here that is on LV with HV short circuit. Here in this case on HV, the rated voltage is 3300 volts and rating of transformer is 33 kVA. That implies the rated current to be applied is 33 kVA by 3300, that is equal to 10 amperes. And come to this case, here the rated current to be applied is 33 kVA by rated voltage. So as here test is performed on LV side, so LV side voltage is 220 volts, so 220 volts, that is equal to 150 amperes. And it is discussed that in short circuit test, rated current is to be applied, and that rated current is obtained at 4 to 5% of rated voltage. And in this case, as the test is performed on HV side, so the rated voltage is 3300 volts, and this 10 amperes is obtained at 4 to 5% of 3300 volts. So VSC is equal to 5% of 3300 volts, which is equal to 165 volts. And come to this case, here the rated current is 150 amperes, and this rated current is obtained at 4 to 5% of the rated voltage. And here as the test is performed on LV side, so the rated LV side voltage is 220 volts. So Vs is equal to 5% of 220 volts, which is equal to 11 volts. Now compare these two. If the test is performed on preferred side, the rated current to be applied is 10 amperes. Whereas if the test is performed on other than preferred side, the rated current to be applied is 150 amperes, which is not readily available. And similarly, if you compare these two voltages, the accuracy of reading this voltage value is very high when compared with the accuracy of reading this voltage. As the accuracy in this case is good, so the results obtained are accurate. Whereas in this case, as accuracy is not good, the results will not be accurate. So here are the problems that we face if the test is performed on other than preferred side. That is, large current source is not readily available and high range meters are required and results are not accurate. So because of these reasons, short circuit test is not preferred to perform on LV side with HV side short circuit, and short circuit test is to be performed on HV side with LV side short circuit. And now let's discuss why UPF wattmeter is used to measure input power in short circuit test. To understand that, let's recall the concept of ideal transformer. In case of no load ideal transformer, input power is equal to output power is equal to 0. That is, in case of no load ideal transformer, the power intake by the transformer is 0. Whereas in case of actual transformer, transformer will drive some power, and that power is used to meet the core losses in the transformer. And whereas in case of loaded ideal transformer, transformer will drag input power at load power factor. And in case of actual loaded transformer, transformer will drag the input power close to load power factor. And let's also discuss a simple concept on load. That is, if load on the transformer is connected, because of this load there will be a current in secondary. And now if load is increased, that is, here load is connected in parallel to the existing load, and let us suppose this load be resistive load of value 5 ohms, and let this load be resistive value of 5 ohms. And when load is increased, that is, when extra load is added in parallel with the existing load, observe that as these two are connected in parallel, the effective resistance value is 5 into 5 by 5 plus 5, which is equal to 2.5 ohms. This implies that by increasing the load, the effective value of the impedance will get decreased. If effective value of impedance gets decreased, the current value will get increased. So if you go on increasing the load, that is, if you go on connecting the loads in parallel, then the effective value of the impedance will get decreased more and more. And if it gets decreased more and more, the current will increase more and more. And this will help you to understand why to use UPF wattmeter. And that you can understand from the Phasor diagram. So if suppose this is the flux and this be the input voltage V1 of transformer, and let this be the induced voltages E2 and E1, and it is known that this will be the no load current I0. When there is no load connected to the transformer, then the primary current of transformer is I0. But when load is connected, extra current I2 dash will flow in the primary winding. So the primary current now is I1, which is equal to vector sum of I0 and I2 dash. But I2 dash is decided by current I2. Let the load be resistive load. Then if this is V2, then I2 will be in phase with V2. And for k is equal to 1, I2 is equal to I2 dash. So I2 will be in exactly opposite to I2 dash. And the vector sum of I0 and I2 dash gives you primary current I1. So the resultant of I2 dash and I0 is I1. If there is no load on transformer, then the primary power factor is phi 0, which is the angle between V1 and I0. But when load is connected, the primary power factor angle is phi 1. So which is the angle between V1 and I1? By comparing phi 0 and phi 1, phi 0 will be greater than phi 1. That implies no load power factor will be less than loaded power factor. And at full load condition, the effective impedance value is very low, which implies the current is very high. That is, let's consider full load. So at full load, the maximum current flows in the transformer, and this short circuit can be considered as the full load condition, because by short circuiting, maximum current will flow in the transformer secondary. That is, I2 will be very high, which implies I2 dash will be very high. If this is high, now the resultant of I2 dash and I0 will be I1, which will move like this, and now the angle between V1 and I1 is further reduced, and if it is further reduced, that is phi 1 will be around 20 to 30 degrees. That implies cos phi 1 will be greater than or equal to 0.6, and which can be considered as high power factor. And from this you can note that by short circuiting the secondary terminals of transformer, full load condition is obtained, because of which there is a maximum current flowing in the transformer, and because of which the primary power factor angle is 20 to 30 degrees, and which implies that power factor will be greater than or equal to 0.6, and which is considered as high power factor. So this primary circuit is high power factor circuit, and to measure the power with good accuracy, we are making use of UPF type of wattmeter in short circuit test. From this circuit you can note that the current is equal to the ratio of voltage to the impedance. So here ISC rated is equal to short circuit voltage by the impedance of the transformer Z01, and ISC steady, that is steady short circuit current, is given by the ratio of rated HV voltage by the impedance Z01. And if you compare this, as short circuit voltage is very low, so ISC steady current is greater than ISC rated current, and the ratio of ISC steady by ISC rated is equal to ISC steady is E1 by Z01, and ISC rated is the short circuit current ISC, which can be taken as I1. That implies ISC steady by ISC rated is equal to 1 by, and here I am taking E1 to the denominator, so I1 Z01 by E1, and this represents the per unit impedance drop. So 1 by per unit impedance drop, and per unit impedance drop can be simply termed as per unit impedance. So ISC steady by ISC rated is I1 is equal to 1 by per unit impedance, and which can be taken as equal to 100 by percentage Z, and that implies ISC steady is equal to I1 into 100 by percentage Z. This is the important relation which is considered in designing of transformer. And now finally, this numerical example will clear the most common doubt on OC test and short circuit test. In this numerical example, it is asked to find the electrical equivalent circuit of transformer by using the open circuit test data and short circuit test data. This is the schematic diagram of transformer. By bringing the secondary side parameters to the primary side, or by bringing primary side parameters to the secondary side, we can obtain the electrical equivalent circuit of transformer. And this is the approximate equivalent circuit of transformer, and this equivalent circuit of transformer is obtained by transferring the secondary side parameters to the primary side. So is why R01 is equal to R1 plus R2 dash, where R2 dash is the transferred secondary resistance, and similarly X01 is equal to the XL1 plus XL2 dash, where XL2 dash is the transferred secondary leakage reactance. So R2 dash is equal to R2 by K square, and XL2 dash is equal to XL2 by K square. And if you transfer primary parameters to the secondary side, then we get the equivalent resistance R02 and equivalent reactance XL02. And it is discussed that from open circuit test we can find the shunt branch elements R0 and X0 of electrical equivalent circuit of transformer, and we can also find the iron loss of the transformer from open circuit test. And from short circuit test we can find the series branch elements of the electrical equivalent circuit of transformer, and we can also find the copper loss of the transformer, and that series branch elements could be R01 and X01 or R02 and X02, depending on the side at which the meters are placed while performing the short circuit test. From this question you can note that OC test is performed on LV side and short circuit test is performed on HV side, which are the preferred sides of the transformer. From open circuit test data we can find the shunt branch elements R0 and X0, and from short circuit test data we must first decide whether we are getting R01 and X01 or R02 and X02. And observe here that short circuit test is performed on HV side, and here HV side is secondary side of the transformer. So from this data we are getting R02 and X02. But to get the equivalent circuit of transformer we need to find R01 and X01. So from R02 we must find R01, and from X02 we must find X01, where K is the transformation ratio constant, which is equal to N2 by N1, which is equal to E2 by E1, where E2 is the secondary induced voltage and E1 is the primary induced voltage. So now by using open circuit test data, this voltage represents the no load voltage V0, and this current represents the no load current I0, and this represents the wattmeter reading W0, which can be taken as equal to the iron loss of the transformer. And it is known that R0 is equal to voltmeter reading by IC, and which is equal to V0 by IC is no load current I0 into cos phi naught, and X0 is equal to voltmeter reading by I mu, that is equal to V0 by I mu is I0 sin phi naught. So to find R0 we need to know V0, I0 and cos phi naught. V0 and I0 are the given data, so we need to find phi naught, and phi naught is found by W0 is equal to V0 I0 cos phi naught. W0 is the wattmeter reading and V0 is the voltmeter reading, I0 is the ammeter reading from the open circuit test data. So we can get phi naught, and by using this we can find R0 and similarly X0, which are the shunt branch elements of the electrical equivalent circuit of transformer. And now coming to the short circuit test data, which is performed on HV side, but HV side is here the secondary side. So by using this data we are getting the series branch elements R02 and X02, but we need to find R01 and X01. So first let's find the R02 and X02 by using this data. So this is VSC and this is ISC and this is WSC, and which can be taken as equal to the copper loss of the transformer. So from the given data, WSC is equal to ISC square into R02. So by using this we can find R02, and Z02 is the ratio of voltmeter reading VSC and ammeter reading ISC. So now after finding Z02 and R02 we can find X02, which is equal to the root over Z02 square minus R02 square. So After obtaining R02 and X02, then we need to find R01 and X01. And now R01 can be found out by R02 by k square, and similarly X01 is equal to X02 by k square. This is how we must find the electrical equivalent circuit parameters by using the test data. Now, Sumpner's test. Sumpner's test is also called as back-to-back test. And before going to know about this Sumpner's test, the knowledge on open circuit test and short circuit test is very essential. And you must be aware of Hopkinson test, and what you must note from Hopkinson test will be discussed here. So there is no need to study the entire Hopkinson test to understand this Sumpner's test. And from this video on Sumpner's test, you will go to know why Sumpner's test is to be used and why it is called back-to-back test, and how to conduct this Sumpner's test, and how to find transformer performance, that is how to find the transformer efficiency and percentage regulation. Now let's discuss why to use Sapna's test. Sapna's test is mainly used to determine the transformer temperature rise. And why to determine the temperature rise in a transformer means, from the safety point of view of the operating person as well as from the safety point of view of the internal parts of the transformer, the temperature rise in a transformer is to be known. Because if the temperature rise is enormously high, the transformer might get exploded like a bomb. So is why most of the transformers are placed outdoor. And secondly, it is used to find the performance of the transformer, that is percentage regulation and efficiency of transformer. And it is studied that from the open circuit test and short circuit test data, percentage regulation and efficiency can be found, but the results that obtained are not accurate. And why percentage regulation and efficiency obtained from the test data of open circuit test and short circuit test is not accurate means, let's discuss in brief. Open circuit test is conducted on LV side with HV open, and here rated voltage is applied, and from this test the iron loss of a transformer are found, and shunt branch elements R0 and X0 of the transformer electrical equivalent circuit are found. And now coming to short circuit test, this test is performed on HV side with LV side short circuit. LV side is short circuit with a thick wire, and here rated current is applied, whereas in open circuit test rated voltage is applied. And from short circuit test, copper loss of the transformer found, and the series branch elements R01 and X01 are found from the short circuit test. And by using the test data from the open circuit test and short circuit test, the transformer efficiency and regulations are found. But the point you must keep in mind that in transformer or in any machine, if you give input, you will get output, and output will be always less than the input because of losses in the machine. And in transformer, the major losses are classified as copper losses and iron losses. So these copper loss and iron losses in transformer exist simultaneously. But from the open circuit test and short circuit test data, we are finding one loss by neglecting the other loss. That is, from open circuit test, we are finding the iron loss by neglecting the copper loss. And from the short circuit test, we are finding the copper loss by neglecting iron loss. So the results obtained from open circuit test and short circuit test are not accurate. Whereas in Sumpner's test, we will find the copper loss and iron losses simultaneously. That is, We are finding the losses which are occurring simultaneously from Sapna's test. And the other reason why to use Sapna's test is, if in case of small size transformer, to find the performance, you will apply the input and you can connect the desired load. And by loading this small size transformer for a particular period of time, by collecting the transformer oil, you can check the temperature rise. But to check the temperature rise of large size transformers, you need to connect the huge load on the large size transformer and you must load it for a particular period of time. That is, large size transformer will consume more input power. Whereas in this case of small size transformer, to determine the temperature rise, this transformer is consuming very little power because of very low load, and that power consumption can be neglected. But to determine the temperature rise of large size transformer, we need to apply more input. That is, here power consumption is very high as we are connecting large load. That is, here to determine the temperature rise, we are wasting large amount of power. So to determine the temperature rise in a transformer without wasting the large amount of power, we are going for Sapna's test, in which two identical transformers are required. If this is one transformer and if this is the second transformer, to this transformer will act as load, and to this transformer will act as load. So in case of Sapna's test, there is no requirement to connect the load because transformer itself acts as load on the other transformer. Therefore, the third reason is to save power. In case of large transformers, temperature rise determination. So these 3 points will tell us why to use Sapna's test. Now let's discuss why Sapna's test is also called as back-to-back test. And why Sapna's test is called as back-to-back test means, in simple statement, one transformer will act as the load on the other transformer. That is, to this transformer will act as load, and to this transformer will act as load. And that you can understand from the circuit diagram of Sapna's test. But it will be little confusing if you observe the circuit diagram of Sapna's test. To understand that, little knowledge on Hopkinson test is required. Let's discuss that. Hopkinson's test is used to find the performance of DC motor, and this Hopkinson test is also called as back-to-back test. And if you can understand why this Hopkinson test is also called as back-to-back test, you can simply understand why Sapna's test is also called as back-to-back test. Hopkinson test requires two similar DC machines. One machine will run as motor and the other machine will run as generator. Let us suppose this machine is acting as motor and let us suppose this machine is acting as generator. If suppose the input supply is given to this DC machine, so as electrical energy input is given to this DC machine, this machine will run as motor. So the output from the DC motor is mechanical energy output. And if you give this mechanical energy output to the generator as input, that is by coupling the shafts of motor and generator, you can provide the mechanical energy input to the generator. And as now this machine is receiving mechanical energy input, this machine will run as generator. So the output is electrical energy. And if the electrical energy output is fed back to the DC motor as input, ideally there is no requirement of this input source, because in ideal case input is equal to output, that is loss are zero ideally. Let us suppose motor requires 10 as input, so by using some external source you apply 10 and then the output is 10 from the motor, and let us suppose this generator requires 10 as input, so this 10 is given to this generator and the output is 10 because we are considering ideal case. And This 10 we are feeding back to the DC motor. So now as this motor is getting output from the generator, there is no requirement of this external source. So you can disconnect this and these two machines will run continuously without any external supply. But is it practically possible to run these two machines without any external source? No, because of losses present in the machines. This requires 10 as input and let us suppose this requires 10 as input. And because of losses, the output from the motor is 7. And this output from the motor is not sufficient to this generator. So here we need to give additional input to this motor to get 10 as output, and that 10 as output is given as input to the generator. Means we need to give the input to the motor which is equal to the losses in that machine. And now by giving the external input to the motor, let us suppose we are getting 10 as output. So this 10 as output is given to the generator, and because of the losses in the generator we will get again output less than the input, and this output is not sufficient to give as input to the motor. So to make the output of generator as input to the motor, again we need to give an additional input to the generator, and that additional input is equal to the losses in that machine. So to make this set run continuously, we need to provide an additional input which is equal to the losses of that machines. That is, here input is equal to the losses of motor plus loss of generator. So if you can now provide input which is equal to the total loss of that machines, now this set will run continuously. And as the output of motor is fed to the generator and the output of generator is fed back to the motor, so this test is called as back-to-back test. And coming to Sapna's test, Sapna's test is also called as back-to-back test because there we are making use of two transformers and one transformer will act as load to the other transformer. So as well, Sapna's test is also called as back-to-back test. And let's understand that with its circuit diagram. This is transformer 1 and this is transformer 2, which are similar transformers, and these two transformer primaries will receive input from the AC input supply through a single phase variac. And to measure the input power taken by these transformers, we are connecting a LPF wattmeter. This is LPF wattmeter. So now the input is given to this primary of the transformer, and the primary of transformer 2 is connected like this, which means primaries of the transformers are connected in parallel, and the power taken by these two transformers is combinedly read by this LPF wattmeter. And the important point that you must make a note here is that the secondaries of these transformers are connected in series with phase opposition. That is, the end point of this transformer is connected to the end point of this second transformer, and the other end of transformer is brought out like this. Means these two are connected in series but they are connected in phase opposition. Means they are connected in subtractive mode, and to connect in phase, the end point of this is to be connected to the starting end of this transformer. But here in Sapna's test, these two transformers are to be connected in phase opposition. So now if you measure the voltage between the starting point of this transformer 1 and the ending point of this transformer 2, then the voltage reading must be 0 if they are connected in series phase opposition. And why they are to be connected in series phase opposition, let's discuss that in the discussion on how to perform this Sapna's test. Now here our focus is why Sapna's test is called as back-to-back test. So let's discuss that. And the secondaries are supplied from an auxiliary source, that is here a single phase variac. And this input is measured by using an UPF wattmeter. So this is UPF wattmeter. And now observe that, let us suppose that input is provided from this side. So this transformer 1 receives the input supply from this side, and as this side of transformer receives power, so this power is transferred to the other circuit, means this side. And for simplicity, let's forget this circuit. And now check that the output of this side is being received by this transformer 2 as input. And as this side of the transformer is receiving power, so this power is transferred to this circuit. And similarly, to make this side simple, let's forget this circuit. And now observe that the output received by this transformer is being fed to this side of transformer 1, which means that the power from this side is transferred to this side, and the power from this side is received by this side, and which is transferred to this side, and the power from this side is being fed to this side of transformer 1, which means one transformer will act as load on the other transformer. Means this transformer's load is this and this transformer load is this. Because of this reason, Sumpner's test is also called as back-to-back test. That is, because of each transformer acting as load on other transformer, this test is called as back-to-back test. Now let's discuss how to conduct this Sumpner's test. We know that this is the transformer 1 primary and this is the transformer 1 secondary, and this is the transformer 2 primary and transformer 2 secondary, and these two transformers are similar transformers and they receive power from the same supply. Let us suppose this is phase and neutral. So this transformer primary is receiving supply like this, and this transformer primary is receiving supply like this, which means transformers primaries are connected in parallel. And to measure the input power, we are connecting an LPF wattmeter, and to measure the input voltage, we are connecting an voltmeter, and to measure the input current, we are connecting an ammeter. And this total circuit is receiving power through a single phase variac, means this is the single phase variac and this is the input AC supply. And the secondaries of these transformers are to be connected in series phase opposition, and if to connect in series and in phase, the end of the transformer is to be connected to this starting end of this transformer. But here we require the series connection of transformer in phase opposition, means this end is connected to this end of the transformer. As now the secondaries of the transformer are connected in series phase opposition, and if you measure the voltage between the starting end and the finishing end of this, you must get the voltage as 0 because they are connected in phase opposition. As these two are similar transformers, the voltage induced here is equal to the voltage induced here, and as these are connected in series phase opposition, they both are equal and get cancelled each other. Means if you measure the voltage between this point and the end point, the voltage must be 0, and to check that, we are connecting an voltmeter. So if the voltmeter reads 0, then we can ensure that these two transformers are connected in series phase opposition. And the important point that you must keep in mind here is that the voltmeter range must be double the voltage rating of this transformer, because if V is induced here and if V is induced here, if they are not connected in series phase opposition, then the voltage between this point and this point will be 2V. Therefore, the voltage range of this voltmeter must be double the voltage rating of this side. And to measure the current, we are connecting an ammeter, and to measure the power, we are connecting an UPF wattmeter here. And the secondaries of these transformers are supplied by an auxiliary source. So let us suppose it is supplied through an single phase variac. So AC input supply, so phase and neutral. This is single phase variac and this is also single phase variac. And if you connect a switch like this, this completes the circuit diagram. Now let's see the procedure to conduct this Sumpner's test. The first step is, with switch as open, That is, with this switch as open, apply rated voltage on primary sides of the transformer. That is, we need to apply the input supply by varying this variac till the voltmeter reaches the rated voltage, and here the rated voltage value is LV voltage. So we need to vary the variac till the voltmeter reaches LV value with switch as open. And once the input supply is applied to this transformer 1 and transformer 2, EMFs will be induced in the secondaries of these transformers. So let the EMF induced in transformer 1 secondary be E2A, and let the EMF induced in the transformer secondary be E2B. And as these two transformers are similar transformers, so E2A is equal to E2B. And as these secondaries are connected in phase opposition, E2A and E2B will be cancelled. That is, if you measure the voltage from this point and the end point, the voltmeter reads 0. If this voltmeter reads 0, this indicates that these two secondaries are connected in series phase opposition. And if you view from this side, this will look like an open circuit test. And many will have a doubt in mind that if voltmeter reads 0, then it is short circuit. So how we can call it as open circuit? And the answer is that if short circuit, the resultant voltage is 0. But the converse is not true. 0 voltage doesn't indicate short circuit. That is, if suppose you are connecting two batteries like this, so these two are connected in series, and if you measure the voltage from this point and this point, the resultant voltage will be 2V. But if you measure the voltage between these 2 points when these two sources are connected like this, then the voltage is 0. And this 0 doesn't indicate that these two are short circuited, right? Here 0 means these two are connected in opposition and these 2 points are not short circuited. There is a lot of difference between the short circuit 0 voltage and this 0 voltage, and this is what happening here. And now let's discuss by viewing from this side how this can be as open circuit test. In open circuit test, HV side is left open and on LV side rated LV voltage is applied. And to measure the input power taken by the transformer, LPF type of wattmeter is connected. And to measure the input voltage, voltmeter V. And to measure the input current, I0, ammeter A. And it is taking supply from a single phase auto transformer. This is AC input supply. As this is open circuit test, that is, as secondary is left open, so current I2 is 0, and because of which transformer will drag very low current from the input supply, that is 4 to 5% of full load current. We know that input is equal to output power plus losses, and the major losses are classified as copper losses and iron losses. And as here open circuit, so current I2 is 0, which means output power is 0. So input can be taken as equal to copper loss and iron losses. And in open circuit test, as the transformer drags 4 to 5% of full load current, which means that copper losses are very low, because copper loss depends on the current. So copper losses can be neglected. So input power can be taken as equal to iron losses. And here we are using LPF type of wattmeter in open circuit test to measure the input power. So as input is equal to iron losses, which implies that this wattmeter reading will indicate the iron loss of the transformer. And the point what you must make a note in open circuit test, that here secondary is left open, means current I2 is 0, that is secondary current I2 is 0, and this is what we are making use in Sapna's test. So as these two are similar transformers, so EMF induced in this secondary winding and EMF induced in this secondary winding are equal and opposite, so they get cancelled, which means voltage is 0, and because of which there will be no current flow in this circuit. So this will resemble like an open circuit test, because in secondary current is 0. So these two transformers will drag very low current, that is 4 to 5% of its full load current, by which we can neglect the copper losses, and therefore we can take input is equal to iron loss of the transformer. And here in this test, wattmeter will read the iron loss of these both transformers. So if you want to know iron loss of this one transformer, you can divide the wattmeter reading by 2. And now the third point is close the switch S only when Vs reads 0. That is, you must close this switch only if the voltmeter reads 0 reading. If it doesn't read 0, which indicates that these two are not in phase opposition. So we must interchange the terminals such that voltmeter Vs reads 0, and once this reads 0, you must close the switches. And now apply rated current by varying variac 2. Now by varying this variac, you must apply the rated current. Rated current I is found by rating of the transformer divided by HV side voltage. And it is known that rated current is obtained at very low input voltage. So you must vary the variac very slowly such that ammeter reads the rated current. And observe that when the input supply is given to the secondaries, now current I flows, and this current I flows through this secondary, and observe the current flow direction in this winding. So these two are opposite, and once the transformer 1 secondary receives power, this power is transferred to the primary side. And similarly, once this transformer 2 receives power, this power is transferred to the side. As these two secondaries are in phase opposition, so the currents in primaries will be in opposite direction, and the currents are limited in this closed loop. To understand that, observe this diagram and let's forget this circuit. So now let the current in this winding be in this direction, let the current in this winding be in this direction, and this can be furtherly simplified like this. So if one winding current direction is like this and the other winding current direction is like this, so observe that now the current will circulate in this loop, which means this current is limited in this closed loop and which will not flow in this wattmeter. Means this LPF wattmeter will continuously reach the iron losses. That is, variation of this supply doesn't affect the wattmeter reading, because by varying the supply, the power which is transferred is limited in this closed loop. It doesn't affect the wattmeter reading. Therefore, wattmeter reading will continuously indicate the iron loss of the transformer. And if you observe from this side, this input power is equal to output power plus losses. And here the output which is on primary side, and there is nothing to consume that output power, means this power is limited in this circuit, which means output power is 0, and the losses that are present are copper losses and iron losses. And we are applying the rated current, and that rated current is obtained at very low voltage, and as iron losses depends on the voltage, and here the voltage applied is very low, therefore iron losses can be taken as equal to 0, which means this input power can be taken as equal to copper losses. And here we are making use of UPF wattmeter to measure this input power, and here as input power is equal to copper losses, which means this wattmeter reading will indicate the copper losses of these both transformers. And if you want to know the copper loss of any one of the transformer, divide the wattmeter reading by 2. Therefore, now the fifth step is, upon applying the rated current, now note down meter readings, and then by using these meter readings, calculate percentage regulation and efficiency. Therefore, if you view from this side, it will resemble like an open circuit test, and if you view from this side, it will resemble like an short circuit test. But this sumpner test is entirely different from the open circuit test and short circuit test. And simply the procedure to conduct this test is that first you must ensure that variac 1 and 2 are at minimum position and switch S is in open position. Now vary the variac 1 till the voltmeter reads rated LV voltage, and now observe the voltmeter Vs reading. If voltmeter Vs reading is 0, then continue for next step, but if it doesn't reach 0, which indicates that the secondaries are not in phase opposition. Then you must interchange the terminals such that Vs reads 0. And once Vs reads 0, now close the switch. And once the switch is closed, now by varying this variac to slowly apply rated current. And once the rated current is applied, now note down all the meter readings. And by using these meter readings, find out the efficiency and regulation. This is how Sapna's test is conducted. Now let's see how to find the efficiency and percentage regulation. Here this ammeter reading is represented with I0 and this voltmeter reading is represented with V0 and this wattmeter reading is represented with W0 and this ammeter reading is represented with ISC and this is represented with WSC and the voltmeter reading here is represented with VSC. Therefore, note down V0 reading, I0 reading, W0 reading, VSC reading, ISC reading and WSC reading. W0 reading represents the iron losses of both transformers and WSC represents the copper loss of both transformers. And it is known from the open circuit test by using these three datas you can find the shunt branch elements R0 and X0. And by using this data you can find the series branch elements R01 and X01 or R02 and X02. And each transformer shunt branch elements are equal to R0 by 2 and X0 by 2. And each transformer series branch elements are equal to R01 by 2 and X01 by 2 or R0 by 2 and X0 by 2. And it is known that efficiency is equal to output power by input power and which can be taken as equal to output power by output power plus losses and which can be taken as equal to output power by output power plus copper loss and iron losses. And output power is the rating of the transformer and WC is WSC by 2 and WI is W0 by 2. So place rating of the transformer and copper loss of each transformer and iron loss of each transformer. This is how you can find the efficiency. And percentage regulation is equal to I2 R02 plus or minus I2 X02 by E2. E2 is the secondary side rated voltage and I2 is the ISC current and R02 and X02 are the series branch elements. And by placing these data values here, you can find the percentage relation. So this is how the efficiency and percentage relation of transformer are found from Sapna's test. Thank you for watching. If you like this video, please like this video, share this video and do subscribe to this channel. Thank you. See you in next lecture.